Hey folks, my name is Nathan Johnston and welcome to Lecture 9 of Introductory Linear Algebra. Today we're going to introduce something called matrix multiplication, which in a sense is the first really new operation that we've introduced in this entire course. We've seen lots of operations like vector addition and even matrix addition, which, while technically they're new and we hadn't seen before, they're so intuitive that it's kind of tempting to say that they're not new, right? They're just the thing that you do entry-wise, right? If you want to add up two vectors, we'll just add up all the real numbers in those vectors. Matrix multiplication, on the other hand, is very, very new, okay? It does not look like any operation that you've ever seen before. It is completely different. Okay, so what we're going to do is we're going to introduce this operation. We're going to go through a couple of examples of actually how to do it to make sure that we understand the computational process. We'll prove a couple nice properties of it, and this is going to be really important this time because these properties are not going to be obvious because the definition is so weird. So it's going to be really, really important that we understand what nice properties this operation has and doesn't have. Okay, and then you're going to be left after this video, I apologize, you're going to be left with a question of why is matrix multiplication defined in this way? And there is a good reason that's defined in this way. We're not going to get to it in this lecture though, okay? It's going to come in 3 or 4 lectures from now. So for now, just take matrix multiplication and bury that question of why in the back of your mind. We're going to get to why, I promise you, but we're not going to focus on that just yet. We'll get to it. Okay, so that's enough of a lead-in. I apologize, I'm not trying to scare anyone. What is matrix multiplication? Okay, so here's the setup. Suppose that you've got two matrices and you want to multiply them. Now, the naive thing you might want to try is just multiplying them entry-wise, okay? And that's a thing you can do, but it's not what we mean when we say matrix multiplication, okay? Matrix multiplication is not entry-wise multiplication. Instead, here's what it is. Suppose you've got two matrices. Don't worry about the sizes just yet. We'll talk more about this later. But then the product of those two matrices is the matrix whose entries are defined in this way. Okay, so the ij entry of the product is this funky sum of product terms here. And what's happening here is all of these A entries, these are coming from the ith row of the matrix A. And all of these B entries, they're coming from the jth column of the matrix B. Okay, so what's happening here is the way you get the ij entry of A times B is this is actually a dot product. You do the dot product of the ith row of A with the jth column of B. Okay, so let's draw a little schematic here to try to sort of pin that idea down and make sure that we understand what's going on. Okay, so here we go. So you've got some matrix A and you want to multiply it by some matrix B to get the product A times B. And the way you do that is, well, you've got to do a whole bunch of computations. You've got to do sort of a separate computation for each entry in this matrix product AB that you want to get. And each one of these entries is a dot product computation. So for example, if you want to compute the 1, 2 entry of AB, right, this entry in the first row, second column, what you do is you do the dot product of the first row of A with the second column of B. Okay, so in other words, this entry here, it's the dot product of this green row with this green column, which is exactly what we wrote over here. Okay, that's that dot product. If you want to get the 3, 4 entry of AB, this one down here, the entry in the third row, fourth column, then what you do is you take the dot product of these rows and columns highlighted in purple, the third row of A with the fourth column of B. In other words, this dot product that we wrote down there. Okay, and then you do this for every single entry in the matrix product AB. So you take every possible dot product of a row of A with a column of B, and eventually you fill out the whole matrix AB. Okay, so that's how you compute the product of two matrices. And again, we'll come back and talk about this paragraph in a minute. Okay, we'll talk about what the sizes of the matrices have to be. But for now, let's just go through an example. Let's actually do a computation here, okay? So I'm just going to make up some random matrices here, and we'll compute some products of them. So A is going to be that 2 by 2 matrix, B is going to be that 2 by 2 matrix, doesn't matter what it is, C is going to be a 2 by 3 matrix. All right, and then let's compute the products here. Okay, so let's start off with the product A times B. Okay, so what we're doing is we're taking dot products of every single row of A with every single column of B. Okay, so the top left entry of the product here of A times B is going to be top row of A with left column of B, dot product. So it's going to be 1 times minus 2 plus 3 times 3, and that's what I wrote here. Okay, top right entry is going to be top row of A with right column of B. Okay, so you just sort of match them up, right? If I want to get the 1, 2 entry, then I do the first row, second column. Okay, so subscripts just sort of in the same order. Okay, so 1, 3 dotted with 1 minus 1, and that's what I wrote there. Bottom left entry is going to be bottom row, left column. Dot them together, you get this quantity. Bottom right entry of the product is going to be bottom row with right column. And again, dot product them. So it's going to be -2 times 1 plus 1 times -1. And you get exactly this quantity here. And now you just actually do those computations in each of those entries. 1 times -2, well, that's -2, plus 3 times 3, that's 9. So you add them up and you get 7. So my top left entry is going to be 7. And you do a similar calculation in each of the other 4 entries. And then we find that A times B is this matrix, 7 -2, 7 -3. All right, so that's our first example of matrix multiplication. Let's do another one. Okay, we can also do A times C, okay? Even though the matrices A and C have different sizes, this product does make sense. So for now, let's just go through the calculation, and then I'll dwell a little bit more on the size issue in a moment, okay? But A times C does make sense, okay? And a quick way to see that it makes sense is, remember, what I'm going to be doing is I'm going to be doing dot products of rows of the first matrix A with columns of the second matrix C. And the rows of A and the columns of C, they have the same number of entries in them, right? This is a vector with 2 entries, and this is a vector with 2 entries. So I can do that dot product. And as long as that's the case, then the product makes sense, right? The matrix product makes sense. Okay, as long as you can do those dot products of the rows with the columns, then everything's good. All right, so here, top left entry is going to be 1, 3 dotted with 1, 3. Top middle entry is going to be 1, 3 dotted with 0, -1. Top right entry is going to be 1, 3 dotted with 2, 4. Now the bottom left entry is going to be -2, 1 dotted with 1, 3. And then the next entry is -2, 1 dotted with 0, -1. Then -2, 1 dotted with 2, 4. Okay, so this time the product is going to be 2 by 3, right? I'm going to get, because I get this top row dotted with each of 3 columns, and then this bottom row dotted with each of 3 columns. All right, so my product is going to look like this. And then again, you just actually do that computation in each of those entries. 1 times 1 plus 3 times 3, well, that's 1 plus 9, that's 10. And similarly for all of the other entries in the matrix. So we find that this is our product here. Okay, our product of A times C is this 2 by 3 matrix in this case. All right, what if we tried to flip that around? What if we tried to do C times A? Okay, well, then what we would have to do is, remember, you do rows of the first matrix dotted with columns of the second matrix. So we would have to do, like for the top left entry, we would do the row 1, 0, 2 dotted with the column 1, -2. Okay, and then alarm bells should start going off in your head, because you cannot do the dot product of a row with 3 entries with a column that has 2 entries. You can't do a dot product between 2 vectors if there are different numbers of entries in those vectors. Okay, so this product here, it just doesn't exist, okay? It's not defined. That is a matrix multiplication that you just cannot do. All right, so let's talk about the size issue a little bit, okay? The way it works is for you to be able to do a matrix product, for you to be able to multiply A times B, well, the first matrix, it has to have the same number of columns as the second matrix has rows, okay? That's the condition that guarantees you can actually do these dot products. Okay, another way of saying this is when you do the multiplication, the inner dimensions have to match up. Okay, so for example, if you tried to multiply a 2 by 3 matrix by a 2 by 3 matrix, doesn't work, because the inner dimensions, the 3 and the 2, those are not the same. You're going to be taking dot products of things with 3 entries with things with 2 entries, and you can't do it. But if you tried to do a 2 by 3 matrix times a 3 by 7 matrix, that does work. Okay, because the inner dimensions, this 3 and this 3 that are sort of on the inside there, they match up with each other. You're going to be doing dot products of things with 3 entries with things with 3 entries, and it all works out fine. All right, let's draw that again, maybe in a slightly different way, just to make sure that we understand what I'm saying here. All right, so what happens is, if you have an m by n matrix, the only way you can multiply by that by some other matrix is if the first dimension of that other matrix is n. In other words, the number of columns of the first matrix matches up with the number of rows of the second matrix. That's the only way you can do that product. Okay, so those inner dimensions, they've got to match. Okay, and then what about the outer dimensions? Well, the outer dimensions, they don't have to match. They can be anything they want to be, okay? So we just call them different letters, M and P, okay? But then what happens with those outer dimensions is they become the dimensions of the product, okay? So if your original matrix has M rows on the left, like the first matrix, A has M rows, and then B has p columns, so your second matrix has p columns, then the product A times B is going to have m rows and p columns as well. Okay? So these m and p, the outer dimensions, give us the dimensions of the product. And the inner dimensions, they've just got to match, but then they sort of get squeezed away. They don't appear in the product anywhere. All right. So, great. Hopefully we understand how to do matrix multiplication now. It seems a little bit arbitrary and weird, but we can do it. Let's go through what sort of properties this new matrix operation has. Okay, what kinds of nice properties do we have to work with? It's a very weird operation, so it's not obvious at first that it has any nice properties, but fortunately it does. Okay, so let's go through what they are. Okay, well, the first one is this property that we've called associativity a whole bunch of times already, okay? And this just means that you can group parentheses however you like. If you do A times B times C and group parentheses between the first two matrices and the last, or, after the first matrix, around the second and the third, you get the same thing. So associativity just means you can group brackets wherever you like in matrix multiplications. Still works, okay? You get the same thing no matter what. We also have distributivity. So if you do a matrix times a sum, you can sort of split that up how you want to, how you're used to doing it with real numbers. It still works actually with matrix multiplication as well. So really, in a sense, like even though this operation looks very weird at first, it really is behaving like multiplication in the sense that sort of it distributes over addition. It plays with addition the way we expect multiplication to play with addition. Okay, and the same thing happens if you multiply by some matrix on the right. It distributes how you would expect it to. You can sort of take the C and split it and sort of distribute it over the addition. All right, and it behaves, this bottom property is maybe less surprising, but it's still nice to have it written down. It sort of behaves well with scalar multiplication as well. So you can do the matrix multiplication and then multiply by a scalar, or you can multiply by the scalar by any of the individual matrices and then do the matrix multiplication. So you can sort of swap the order of scalar and matrix multiplication, and the result doesn't change, okay? You get the same answer either way. All right, so what we're going to do is we're just going to prove property B of this theorem. You can prove all of the other properties of the theorem in the exact same way, but it's just going to come down to write down the definition of the thing, simplify it and expand it out, and then, oh yeah, this equals this. All right, so let's see how it's done. Let's go through the proof of property B. All of the rest are similar. All right, so property B, maybe I'll scroll up so that's actually still on screen there. So property B, it's this left distributivity property. Okay, so just to give us sort of some concrete notation to be able to use throughout the proof, I'm going to give sizes to these matrices because that's actually not specified in the statement of the theorem itself. So I'm just going to suppose, hey, A is m by n, and then B and C are both going to have to be n by p for these matrix multiplications to actually make sense in the first place, right? We need the n here and the n here to match up. That's all I'm saying. All right, and then let I be some index of a row, and let j be some index of a column. So I'm going to look in the ij entry of this matrix and show that those are the same, no matter what I is and no matter what j is. All right, so let's do that for the matrix on the left, A times B plus C. We're going to look just at the ij entry of it, where I and j are just anything, okay? They're just specify some entry of that matrix. And well, just by definition, the ij entry of a matrix product is, well, it's the dot product of the ith row of A with the jth column of B plus C, right? Remember, that's our ugly definition of matrix multiplication. So that's what I've written down over here. It looks ugly, but that's all it is. It's a dot product. Dot product of the ith row of A, right? All these entries are coming from the ith row of A, and the jth column of B plus C. And that's where all of these entries are coming from. These are the entries in the jth column of B plus C. And notice that whenever you write down a sort of a sum coming from a matrix multiplication, the inner dimensions match, okay? And you add up over all possible values of the inner dimensions. So the outer dimensions here, this are I and j. Those are the entry of the product that you're looking in. So I is my leftmost dimension, j is my rightmost dimension, or subscript, and then the inner subscripts, well, 1, 1, 2, 2, n, n. So they always match, and that's the one that I'm adding up over. Okay, great. Next thing I'm going to do is I'm going to say, hey, well, this is just a sum and product of a whole bunch of real numbers. I know how real numbers behave, right? I know all the nice properties that they have. In particular, I can split that up into, like, I can distribute over each one of these parentheses, right? I can distribute here, and distribute here, and distribute here. And when I do that, I get AI1 times B1j plus AI1 times C1j, right? These first two terms are coming from that first parenthesized term. Okay, and then when I distribute out this term here, now I get these two terms, and so on. So that's all I'm doing, is I'm using distributivity n times. Okay, and then I'm going to stop there, okay? That's sort of as simple and as expanded out as I can make this expression. So now I'm going to jump ship, and I'm going to say, okay, great, that's what the ij entry of the left-hand side equals. What does the ij entry of the right-hand side equal? Okay, and my hope here is that it equals the exact same thing, because if it equals the exact same thing, then yeah, I know these matrices are the same. All right, well, the ij entry of the right-hand side, well, okay, ij entry of a sum of two matrices is just by definition the sum of the individual ij entries. Right, matrix addition is defined entry-wise, so that's all I've done here. I used the definition of matrix addition. Next, I've got the ij entry of this matrix product and the ij entry of that matrix product. So now I'm going to use the definition of matrix multiplication twice. Okay, so this ij entry, well, it's the dot product of the ith row of A with the jth column of B. And that's what I wrote down here. And again, notice mechanically the way this works out is my outer subscripts are always I and j. Okay, because that's the entry in the product that I want. And the inner subscripts always match, and I add up over all possible values of that matching inner subscript. Okay, and then the ij entry of A times C, well, again, that's just the ith row of A dotted with the jth column of C, and that's what I wrote down here. Okay, and now the rest of the proof is just staring at these quantities. Okay, I look at this quantity here, and I look at it really, really, really hard, and I convince myself that, yeah, it's the same as this quantity down here, right? You just match up terms. I've got an AI1 times B1j. Oh, here's an AI1 times B1j. So this term and this term match up with each other. Here's an AI2 times B2j. Oh, well, here's an AI2 B2j. So yeah, that term is in both of the sums. And this happens for every single term, right? There are 2n terms in this sum, and they match up exactly with the 2n terms in this sum. So they're the same. Okay, so the rest of the proof is just proof by eyeballs. You look at them, yeah, they're the same, so great. And then we conclude that, yeah, the matrices must be the same as well, because there's nothing special about I and j, right? They're just some particular value. So hey, if the ij entry is always the same as the ij entry, like if the ij entries on both sides are always the same, no matter what I and j are, well, they're the same matrix. They have all the same entries in the same spots. And then that's it. Then you're done. All right. Now, there's one very important thing about this theorem, and this very important thing that we sort of haven't talked about this theorem yet is something that is missing. Okay, all of the other previous theorems that we've looked at that identified important properties of operations that we introduced, they had a property called commutativity. Okay, right? This property that you could do the operation in either order. So like for example, for vector addition, if you do v plus w, well, that's the same as w plus v. For matrix addition, a plus b is the same as b plus a. You can do it in either order. For the dot product, v dot w is the same as w dot v. All these operations had commutativity, but we didn't write that down for this new operation, right? We did not write down that a times b is the same as b times a. Why not? Well, the reason why not is that it's not true. Okay, matrix multiplication is not commutative. So even though we call it multiplication, it sort of behaves not like real number multiplication in that sense. Okay, so be really, really careful with it. Let's go through a couple examples. Okay, so just making up some matrices here. A is 2 by 2, B is 2 by 2, C is 2 by 3, and D is 3 by 2. Let's do some matrix multiplications here. All right, so A times B, all right, just using the definition, right? These are just, so for example, top left entry is first row of A dotted with first column of B. That's what I wrote down here, and then you just compute all these things, okay? So top left entry is going to be 2 plus 0, oh, it's just 2. Similarly for all the other entries, so that's A times B. B times A, now remember, like it's always you're taking rows of the first matrix dotted with columns of the second matrix. So now B is the first matrix. So now it's rows of B dotted with columns of A. All right, so for example, the top left entry is 2, 1 dotted with 1, 3. So that's 2 times 1 plus minus 1 times 3. Top right entry is going to be first row of B dotted with right column of A. So 2 times 2 plus minus 1 times 4. Okay, and similarly, bottom row with left column, then bottom row with right column. Okay, and that'll give me the 4 entries. And when you actually compute those, you get this matrix now. So minus 1, 0, 9, 12. Okay, and that shows that matrix multiplication is not commutative, right? Because the point is these two matrices are not the same. A times B does not equal B times A. I mean, certainly there are special cases. There are some matrices A and B for which A times B equals B times A, but it's not true in general. It's not a fact about matrix multiplication that you can make use of, okay? It's not a general fact. Okay, so there are counterexamples. Okay, and actually, I mean, most matrices are counterexamples. I didn't have to like specially cook up these matrices to get this counterexample or anything like that. If you just pick random matrices, odds are they're not going to commute with each other. A times B is not going to be the same as B times A in most cases. Okay, and actually even worse than this, not only might A times B not equal B times A, but well, if you were to do A times C, that would exist. That's the thing, right? This is 2 by 2 times 2 by 3. The inner dimensions are both 2. So you can do that matrix multiplication. You'll get a 2 by 3 answer, 2 by 3 matrix as your answer. Okay, but C times A does not exist. So if you try to commute them past each other, something's going very, very wrong because you get something that doesn't even make sense. C times A, well, that's 2 by 3 times 2 by 2. The inner dimensions there are 3 and 2. They don't match, so that matrix product is not a thing. All right, so commutativity fails very hard in that case. And maybe even weirder than that is, well, if you did this product C times D, well, that exists because it's 2 by 3 times 2 by 3 times 3 by 2. The inner dimensions are both 3, so you can do that matrix product. And you'll get a 2 by 2 matrix as an answer if you do C times D. But if you do it the other way around, if you do D times C, again, the inner dimensions match. Okay, it's going to be 3 by 2 times 2 by 3. The inner dimensions are 2 in this case, so they match. Great, you can do the product. But this time the outer dimensions are 3, so the result is going to be 3 by 3. All right, so in this case, if you do CD and DC, well, they both exist, but this time they're not even the same size. Okay, so matrix multiplication is very, very not commutative, okay? And we'll come back in a couple lectures and talk more about why that is. All right, for now though, let's think about a couple of consequences of this non-commutativity and focus a little bit on why we have to be careful with this. So for example, we've talked about, how with the dot products, you can sort of FOIL, right? I mean, you can expand out parentheses in the same way that you expand out parentheses when you multiply real numbers together. Okay, but if you try to do that with matrix multiplication, you have to be very, very careful. Okay, so let me ask you a question here. Does A plus B squared, in other words, A plus B times A plus B, that's what this means on the left, A plus B times A plus B, does that equal A squared plus 2AB plus B squared, right? I mean, if A and B were both real numbers, then this would be true, but the understanding here is that they're matrices. Is this still true if they're matrices? Okay, well, let's just expand things out and check it. Okay, what this means on the left is A plus B times A plus B. Okay, now let's just expand that. We can still expand things out because we have these two left distributivity and right distributivity properties from that theorem that we had up above. And what we get when we expand this out is first times first, so we get A squared, plus first times last, which is AB, and then last times first, which is BA, and then last times last, which is B squared. Okay, so that's true. This does equal this. A plus B squared, you can expand it out to this. But then what we do with real numbers to sort of simplify this down to this, right, to combine the two cross terms, is we have to use commutativity, right? We use the fact that for real numbers, AB equals BA, and we can combine that into just 2AB. For matrix multiplication, you can't do that. Okay, it's something that you've done under the hood without even really thinking about it for years now, and you gotta be really careful with matrices to unlearn that. You can't combine the cross terms. AB is not the same as BA in general. So for matrices, this is not true. Okay, instead, the expanded form has to be written like that. Okay, and there are a few other cases you have to be careful as well, and I'll try to point those out as we come to them. All right. To round out this lecture, we're just going to introduce a couple of special matrices and then one special class of matrices that behave very well with matrix multiplication, okay? And the first two special matrices that we're going to introduce are called the identity and zero matrices, okay? And they're denoted by I and 0, okay? And the way to think about these is basically they're the matrix versions of the numbers 1 and 0, okay? So what does the number 1 have? Like, what makes the number 1 special? And, well, what makes it special is that if you do any number times 1, that number doesn't change. Like, if you do x times 1, you just get x. All right, so that's also going to be what makes this identity matrix special, okay? If we do any matrix times the identity matrix, we're just going to get the original matrix back, okay? It's not going to change. So let's see an example of that, okay? So first off, what is the identity matrix? Well, it's just the matrix that you get if you just slap zeros everywhere in the matrix except ones along the main diagonal. In other words, ones in every entry where the row and column index are the same. So like a 1 in the 1 1 entry, and 2 2 entry, and 3 3 entry, and so on. Okay, so so for example, the 2 by 2 identity matrix is this guy here. It's got a 1 in the 1 1 entry and the 2 2 entry, but then just zeros everywhere else. Okay, well, there's also a 3 by 3 identity matrix. Okay, and that has a 1 in the 1 1 entry, 2 2 entry, 3 3 entry, and then zeros everywhere else. Okay, we could also construct a 4 by 4 identity matrix. It would have 4 ones, 1 1 entry, 2 2, 3 3, and 4 4 entry, but then zeros everywhere else, and so on. So you can construct an identity matrix of any square size. Okay, great. And I mean, zero matrix is actually easier than this. Zero matrix, you can construct a zero matrix of any size that you like. Okay, it doesn't even have to be square, and you just throw zeros everywhere in the matrix. All right, and let's do a quick matrix multiplication example with the identity matrix. Okay, so I'm just going to make up a random matrix A here. So if A is 2, 3, minus 1, 4, let's multiply it by the 2 by 2 identity matrix, just because that's the only one that we can actually multiply it by, right? We can't multiply it by the 3 by 3 identity matrix. The sizes don't match up. All right, so if we do A times the identity matrix of the appropriate size, then what we get is, okay, it's going to be rows of A dotted with columns of the identity matrix. So 2, 3 dotted with 1, 0. Okay, 2, 3 dotted with 1, 0. And then 2, 3 dotted with 0, 1. 2, 3 dotted with 0, 1. And then minus 1, 4 dotted with 1, 0. Minus 1, 4 dotted with 1, 0. And then minus 1, 4 dotted with 0, 1. Minus 1, 4 dotted with 0, 1. And then you just compute all of those things. Top left entry is 2 plus 0. Top right entry is 0 plus 3, and so on. And when you do that, you're going to see that, oh, well, I get the matrix 2, 3, minus 1, 4 after I simplify that matrix multiplication down. And then I stare really hard, and I notice that, hey, oh, this matrix here, well, that looks an awful lot like that matrix there. Isn't that neat? Okay, and also, if I do the matrix multiplication in the other order, okay, so now I'm doing rows of the identity matrix dotted with columns of A. So 1, 0 dotted with 2 minus 1. That's my first entry. Top right entry is going to be 1, 0 dotted with 3, 4, and so on for the other entries. Okay, and then again, you just simplify that down, you do the calculation, and you're going to see that you get 2, 3 minus 1, 4. And again, that looks an awful lot like A. Isn't that neat? Okay, and this happens in general. So we're going to state this as a theorem. Okay, so here's the theorem. Suppose you've got just any old matrix of size m by n. Okay, so it doesn't have to be square, it's just some matrix. Well, then if you multiply it on the right by an identity matrix of appropriate size, so you can actually do that matrix multiplication, you just get A back, okay? So really, multiplying on the right by an identity matrix does nothing. And same if you multiply on the left by an identity matrix of the appropriate size, so the matrix multiplication makes sense, you just get the matrix A back again, okay? Again, it does nothing. Okay, and then the zero matrix does a similar thing, except it just squashes everything down to 0. A times the zero matrix is the zero matrix. 0 times A is the zero matrix, okay? And that one's less surprising, okay? I mean, if you multiply everything by zeros and then add up a whole bunch of zeros, yeah, you're going to get the zero matrix. All right, so really the interesting piece here is the identity matrix. The point is the identity matrix, it acts like the number 1 acts, right? If I do a number times 1, I just get that number. Identity matrix does the same thing for matrices. And we're not going to prove that theorem, but I mean, you could prove it. You just have to sort of muck around with matrix entries for a while. Okay, there's nothing fancy or complicated with the proof. It's just ugly, so we're not going to do it. All right, and then the last thing that we're going to introduce in this class is a family of matrices called diagonal matrices. Okay, and the reason we're introducing these matrices is because they behave really, really well with matrix multiplication. They make us happy. Matrix multiplication in general is a really ugly thing, right? But if we only look at these matrices here, then actually it's a really nice thing. Okay, everything works out way easier. All right, so a diagonal matrix, all we mean by a diagonal matrix is you have some entries on the main diagonal. Again, those are the entries where the row and column index match. So like the 1, 1 entry, 2, 2 entry, 3, 3 entry, and so on. But then every other entry has to be 0. Okay, so for example, this matrix here, this matrix A, 2, 3, that's diagonal. Okay, here's the diagonal entries, they're 2 and 3, and everything else is 0. This matrix here, this is also diagonal. Here's its diagonal entries. They can be whatever they want to be. But the point is the off-diagonal things, those are all 0. All right. Here's another example. Here's the 3 by 3 example. Okay. The point is it has something on its diagonal. Don't care what it is. But then everything off of its diagonal, those are all zeros. That's the important piece. Okay. The fact that I've got a middle 0 entry here in the 2, 2 entry, that's irrelevant. That could have been anything. The point is just, yeah, it can be 0, but it doesn't have to be on the diagonal. Okay. So I could have had 1, 2, 3 here. I could have had 7, minus 5, 9 here. It doesn't matter. Diagonal can be whatever it wants. But these 6 entries all have to be 0 for it to be diagonal. Right? And let's just do a quick matrix multiplication example here to sort of get at what I'm trying to get at here. Okay, so if I do A times B here, okay, rows of A dotted with columns of B. So 2, 0 dotted with 4, 0, and then 2, 0 dotted with 0 minus 2, and then 0, 3 dotted with 4, 0, and 0, 3 dotted with 0 minus 2. Okay, and then you just go through and simplify all of that, right? 2 times 4 is 8, plus 0 is 0, so I get 8 in the top left entry. 0 plus 0 in the top right, 0 plus 0 in the bottom left, and 0 plus minus 6 in the bottom right. Okay, so I end up getting this matrix here. And notice that that matrix is also diagonal, right? I still got zeros in the off-diagonal entries. But moreover, what are these diagonal entries? How do they relate to the diagonal entries of the original matrices? And the point is, 8, well, that's just the entry-wise product of 2 and 4, right? That's just the product of these diagonal entries. And then minus 6, well, that's just the product of these diagonal entries. That's the product of the 3 and the minus 2. Okay? So in other words, if the matrices that you have are diagonal, then the matrix product of those two matrices is exactly the same as the entry-wise product. Okay? So you can just compute the product much more simply, sort of the naive way that you wish you could compute matrix products in the first place. Okay, so the more general fact is this. Suppose you've got any two diagonal matrices. So here's like your diagonal matrix A, here's your diagonal matrix B, and you multiply them together. What you get is, well, you get the diagonal matrix that has just the entry-wise products here. You're going to get A11 times B11 as your top left entry, and then A22 times B22 is your next diagonal entry, and so on all the way down the line. Okay, so if you've got diagonal matrices, then everything works out wonderfully. And we're going to see that's really important later on in the course. What we're going to do is we're going to try to find ways of turning multiplication of arbitrary matrices into multiplication of diagonal matrices. We're going to try to sort of transform matrices into diagonal ones, or at least as close to diagonal as we can get them. Okay, so that is enough for today. I apologize, this was a much longer lecture than usual, but it's also a very important one. It's important that you are able to multiply matrices together because we're going to be doing this for the rest of the course now. Okay, anyway, I will see you next lecture when we start talking about other things, in particular, the transpose of a matrix. So I will see you then.